Hi everybody, now we're talking about smoothing the time series. So we start with simple moving average. And how do you calculate that? You just take the unweighted average of a certain number of the most recent data points you have. So for example, the five period simple moving average is the unweighted average of the five most recent data points prior to and including the current period. And including, okay? So for example, if you have if you want the simple moving average number, so this is just a number, you take the data for the 5 last periods and you just find the average, okay? You divide by 5. So for example, how does it work in practice? So we have some price data, and we have one price per day, probably the end of day price. Then if you have the 5-day simple moving average, then you would not be able to calculate that here because you only have the YT. Okay, so when you move to the next day, you can't really calculate that either because you only have the YT and the YT minus 1, right? But when you get to 8th of January, then you have 5 historical and present day data points. So here you can calculate this, and you can do like this. You find the YT, it's 129, plus YT minus 1, which is 129, and YT minus 2 is 133. YT minus 3 is 134. And the last one is 128. That's YT minus 4. Okay, that's the price 4 days ago. And to find the average, you just divide by 5, okay? And then you get 130.6. And if you go to the next date, you get 131. And when you go to the next date again, you get 130.4. And you just take the average of the current day's price plus the 4 previous prices to get a 5-period simple moving average. So this is how you do it in practice. And for example, here we have taken a chart from stockcharts.com, and we have added a 5-day moving average, which is the blue line, and we have a 20-day moving average, simple moving average, which is the red line. Okay, so what you can see is that the blue line, the 5-day moving average, it's hugging the daily price process quite snugly, right? Whereas if you add more lags, then you get a more smooth process, okay? And you can see that, for example, here the price process is dropping, and the shorter moving average, it's dropping off before the long moving average. Okay, so so you get a fast speedboat is the short moving average, and an oil tanker is the longer moving average. It really takes time to change the course. Okay, so the more terms which are averaged, the smoother the process, but the longer time a signal needs to be detected. Okay, so what about the exponentially weighted moving average? Okay, the exponentially moving weighted moving average is a weighted average of past observations with geometrically declining weights. And what is that? Well, geometrically declining weights is that the weight is, we just say it like this, the weight is geometrically declining. It means that it's multiplied. So the weight of the last observations, they are not equal. For example, if you look here, this is the same as saying 1/5 times 129 plus 1/5 times 129 plus 1/5 times 133, and so on. Which means that for a simple moving average, all the observations are given the same weight, in this case 0.2, 1/5, you know. And after you have included these 5 data points, the rest of the data points, the older data points, they are given a weight of 0, right? Whereas for the exponentially weighted moving average, the weight of the observations, they are like 1/2 plus 1/1/2 squared, okay, which is 1/4, plus 1/8 plus 1/16 plus, and so on. So you see that the weight of the data point is lower the older the data point is. So for example, if you have some data for 20 days ago, then that 20-day price is given a very low weight compared to a more recent price. So, and this exponentially weighted moving average can be written as the average exponentially weighted moving average for time t. Okay, that's the S. It's given as 1 minus the weight, the W, times the, for example, price at time t, plus the exponential weighted moving average at time t minus 1. Okay, last period. So times the weight. Okay, so this means the current smooth value, today is the weighted average of the current data point and the prior smooth value. Okay, and the choice of W affects the level of smoothing. So if W is higher, close to 1, then the more weight is put on the prior smooth value, and not so much weight is put on the current price signal. Okay, but the higher the weight on the prior smooth value, the smoother the process will go, or the smoother the exponential weighted moving average is, and the longer it takes for the exponential smoothing average to actually react to signals in the market. So this gives us the question: how do you pick the weight? And that actually depends on the application. And what you often would do is to compare different weights and look for what kind of signal they are giving you. Okay, so in finance, it's common to pick a number of days and set W equal to this weight, and this is actually quite popular. So, for example, for a exponentially weighted moving average with 5 days, the W is 5 minus 1. That's supposed to be 1, divided by 5 plus 1. Okay, which is 4 divided by 6, which is just 2/3. Okay, so the number of days in the exponential moving average, or the average day of the weight, is given by this formula. And later we are going to look at a 20-day exponential moving average. So then you would have 20 minus 1 divided by 20 plus 1, which is 19 divided by 21, which is closer to 1, right? 19 over 21 is much closer to 1 than 2 over 3, okay? So we would expect the 20-day exponentially weighted moving average to give a smoother curve than the 5-day exponential moving average. And we can see that here, that the 5-day exponential moving average, it follows the price process quite snugly, and the exponential moving average with 20 days, which is the average weight of the days, then you have a much more gliding or smooth curve. Okay, so the larger the N, the higher the W, the smoother the time series. Okay, and the smoother the time series, the more it's trailing behind the observations. Okay. So if we compare these two, then for example, we have a 20-day moving average, and we have a 20-day exponential moving average. And we can see that the exponential moving average, it reacts quicker to price changes than the simple moving average, and that the exponential moving average is more sensitive than the simple moving average. This is quite useful to know, because if you look at the drop here in prices, the exponential moving average is actually reacting to this drop faster than the simple moving average. So they are not equal in that sense. So, for example, and actually one thing I wanted to just mention is that this simple moving average, it's both the simple moving average and the exponentially weighted moving average, they are using historic data, which you know at the time when you get the price. Okay, so for example, you are at 8th of January here, and you want to calculate the simple moving average, and you get the close price from the market, and then you can actually calculate the simple moving average value here. And we do not use any future information. In the market, that would be cheating, right? And often impossible to know. So, for example, seasonal adjustment means that you remove the seasonal component of a time series. So remember that you have a time series which you can decompose into trend, into seasonality, and into remainder. Okay, so if you want to adjust the time series to get the trend, you have to remove the seasonality and the remainder. It's often easier to remove the seasonality before anything else. So, for example, the difference between the observed time series and the seasonally adjusted time series, between the observed time series, which is often like this, and the seasonally adjusted time series, which is often like this, with no ups and regular ups and downs, would be the difference between these would be the seasonal component. And a lot of time series, they are seasonally adjusted already when you get them. For example, if you look at gross domestic product, the value of what's produced in a country, then you can often see a quite strong seasonality, because GDP, it's increasing if people are buying lots of stuff, and it's decreasing if people are starting to save. Okay, so you can, for example, see the Norwegian GDP here at ssb.no, and what's the point of seasonally adjusted time series? Well, it's basically such that you can compare the development in the time series from period to period without thinking, okay, is this because of the season or not? So, for example, in the national accounts, you get the seasonally adjusted 3-month volume growth for GDP of mainland Norway, and because each and every one reader of this statistic should not have to adjust the number for seasonality. So they have done this for you. So, for example, if we look at some U.S. numbers, this is gross domestic product for Norway. Let's see. Okay, yeah. Let's see, 2006, 2019. Gross domestic product for Norway, not seasonally adjusted. Looks a bit low, but yeah. Anyways, the point here is that the blue line, it's not seasonally adjusted, whereas the red line is seasonally okay. So what you see here is that basically every 4th quarter you get this spike, okay, around Christmas time. Okay, so you get this spike, and then you get the trough here, and what you see is that the seasonal this is 4th quarter. Okay, the seasonal process, or the seasonal GDP is flattened such that you should only have the trend and the remainder. Okay, so not seasonally adjusted contains trend plus seasonality plus remainder. Okay, so this remainder, it has many names. We also call it the random factor, or the irregular factor. And the seasonally adjusted graph or numbers, they contain the trend plus remainder. Okay, so you see that if you were to compare 2 consecutive months, for example here and here, you would look at you would want the trend, right? The underlying trend, with as little noise as possible. And what you see here is that you have an upward sloping pattern, but if you had seen or or looked at the non-seasonally adjusted numbers, then you would have had this tiny spike in the data, and then you might have thought that well, the GDP is on a downward slope, whereas it's actually on an upward slope. So, and the case study for today is for the next video.